A binary search tree can degenerate into a chain. What if we add a random priority to each node and maintain heap order? That gives us a treap. Treap is a portmanteau of tree and heap. It satisfies both BST and minute heap properties simultaneously. First, the BST property. For every node, keys in the left subtree are smaller, keys in the right subtree are larger. This guarantees sorted in-order traversal. Second, the heap property. Each node's priority is no greater than its children's priorities. This controls the tree's shape, driving it toward balance. Key insight. If both keys and priorities are distinct, the tree satisfying both properties is unique. Random priorities keep the tree balanced in expectation. Each node has two values, key and priority, shown as key priority. Node 5, 2 is the root because it has the smallest priority. 3, 7 hectares, key less than 5, so it goes left. 7, 3 hectares, key greater than 5, so it goes right. Both have priorities larger than the parents too. Continue adding 2, 9 and 7, 3. Since 7, 3 hectares a smaller priority than 8, 5, it must become the parent of 8, 5. By key order, both still belong on the right of 5. Now insert node 4, 1. By BST rules, key 4 goes as the right child of 3, but its priority is 1, smaller than even the root. To fix the heap property, we rotate. Node 4, 1 is the right child of 3, 7, so the first step is a left rotation at 3, 7, lifting 4, 1 above 3, 7. Now 4, 1 is the left child of 5, 2. A right rotation at 5, 2 makes 4, 1 the new root. Rotations never violate the BST property. They only reshape the tree. Average insertion time is big O of log n. Deletion is the reverse of insertion. To delete a node, rotate it down to a leaf position, then simply remove it. When deleting 7, 3, it has only the right child 8, 5. A left rotation lifts 8, 5 upward and pushes the target node 7, 3 toward a leaf position. Once the target becomes a leaf, just remove it. The remaining tree still satisfies both BST and heap order, and average time complexity is also big O of log n. Why does random priority keep the tree balanced? Key theorem. A treap structure is equivalent to inserting keys into a plain BST in order of increasing priority. If priorities are random, this is equivalent to a random insertion order, and a randomly built BST has expected height, big O of log n. No complicated balancing rules needed. Randomness itself provides probabilistic guarantees. Split divides a treap by a key into two trees. L contains all keys less than or equal to the given value. R contains all keys greater than it. The implementation is recursive. If the root's key less than or equal to the split value, the root and left subtree go to L, then recursively split the right subtree, otherwise vice versa. Merge is the inverse. Combine two treeps into one, given that all keys in L are less than all keys in R. Recursively, the root with the smaller priority stays on top. With split and merge, insertion and deletion can both be expressed through them. Insert equals split T, key plus new node plus 2 merges. Deletion usually uses 2 splits around key, -1, and key to isolate the target, then merges the remaining parts. Implicit Treap is the most powerful treap variant. It doesn't store keys explicitly. The in-order position serves as the implicit key. Each node maintains a subtree size. This lets us find the kth element by index. If parent pointers are also maintained, we can compute a known node's actual position by walking upward. Both are expected big O of log n. This enables efficient array-like operations. Insert, delete at any position, only needs size. Range reversal additionally needs a lazy reverse flag, and range sum additionally needs a subtree aggregate. That is why implicit treap is common for sequence maintenance problems. It can split and concatenate like a balanced tree, while extra metadata gives it some segment tree-style range abilities. Treap combines BST and heap with random priorities, achieving expected balance in the simplest possible way. Just two operations, split and merge, unify insert, delete, concatenate, and split by key, making the code concise yet powerful. And implicit treap extends its power further, becoming the ultimate tool for sequence problems.